In section 4.6, we're going to do problems called related rates. These are going to be application problems dealing with implicit differentiation. So we're going to try to use implicit differentiation. That's section 3.8 material, or I should say section 3.7 material, to solve problems involving finding a rate of something, or we're going to relate the rates by finding an equation that relates those quantities. So let's talk about these steps we're going to have for these problems. These are going to be often confused with optimization problems because they're both involving word problems, but they are very much different, and they're asking for completely different things. And in fact, once we kind of get past the first difficulty of the problems, getting used to them, these problems are really much more straightforward than the optimization problems. It's going to be kind of the same thing every single time. There's really only one thing that's going to change per problem, and that is what equation are we using in each. So I do want to make very clear this is very much different than the optimization problems, although they both are word problems that are historically difficult problems. All right, so what we're doing is we're doing application problems involving implicit differentiation. We're going to see that this differentiation is going to be with respect to t, and we're actually going to have two different variables outside of t that we have to work with. Our Leibniz notation is going to be very important in this section. So our steps: draw a picture if possible, identifying the variables. That's like trying to understand the question. One thing we can do past that is we know we're going to have two, maybe three variables we're looking for. Let's just say we have two. One of the variables we're going to be looking for the rate of change of, and one we're going to be given the rate of change. And that's going to kind of tell us exactly what our two variables are going to be. And we'll see a couple examples that we show exactly that. Once we've identified the variables, we need an equation that relates the two variables. We're going to take that equation and we're going to take the derivative of both sides with respect to t. This is the implicit differentiation. And we're going to do d dt of both sides. After we've taken the derivative, and it is important that we do after the derivative, we're going to have our unknown. We're going to plug in all the remaining values, which are going to be given in the problem, and then solve for our unknown. So what's different from problem to problem is step 2. That's really what's going to change from problem to problem, other than the actual derivative that we have to do, but that's chapter 3 material there. So let's see an example. We're going to start by just explaining this example in general, and then we'll go through the step-by-step process. So air is being filled into a spherical balloon at a rate of 5 centimeters cubed per minute. Determine the rate at which the volume of the balloon is increasing when the radius is 10 centimeters. So there are two different variables here that we're concerned with: volume and radius. And both those values are changing with respect to time. We're going to be pumping air into the balloon. That's going to increase the volume of the balloon. And at the same time, it's going to increase the radius of the balloon. But it's going to do so at different rates. And we're going to try to figure out how can we relate those rates together. There is some kind of relationship between the volume and the radius. How do we find that relationship? And one thing we have to be careful of is that these values, volume and radius in this example, are changing with respect to time, which means they are functions of time, just as y equals f of x is a function of x. So for example, we could graph these functions over t, like here's v. We might have that the volume of the balloon is going, up as t is increasing, right? And the radius, same thing, might also be going up, might be going up at a different kind of level. These are two functions of t. So when we take the derivative of those functions, we do the derivative of v of t, we need to use the chain rule and do it implicitly. Or I should say, when we do like the derivative of v of t like squared, note this is just going to be the derivative of v, which we can write as dv dt, or if you want, v prime. Same thing with r, the derivative of r of t, we're going to write as dr dt, or r prime. So when we want to do the derivative, this is what I meant before, the derivative of, say, v squared, that's when we have to use the chain rule and write this as 2 times the inside function times the derivative of the inside function, as that is like this whole function squared. We'll see that on the next page going through this, but that's kind of a difficulty we have to get over, is that these quantities, these variables, are functions of t. In all of these problems, related rates, chapter or section 4.6, we're going to be looking for the rate of change of one of the variables. That's going to be what the question is asking for. We can see it right here in this question. Determine the rate at which the volume of the balloon is increasing. That means that we want to find dv dt. That is the rate of change of the volume. We're also going to be given a rate in the problem, or maybe 2 rates depending on how many variables we have. So here we have that the air is being filled into the balloon at a rate of 5 centimeters cubed per minute. And I actually realize there's a mistake right here. This should be the radius, because we are given dv dt. We actually want to find dr dt. So the air is being pumped in the balloon at a rate of 5 centimeters cubed per minute. That means that the volume is increasing by 5 centimeters cubed per minute. We want to find the rate at which the radius of the balloon is increasing at the point when the radius is 10 centimeters. And we'll get to this point when the radius is 10 centimeters. That's going to be something we do at the very end of the problem. In order to get through all of this, we need some equation that relates our 2 variables together, v and r. And in this case, we can use the equation, the volume of a sphere, v equals 4/3 pi r cubed. And for each problem we do, the equation we have to use is much different. We could use some area formulas, some volume formulas, the Pythagorean theorem we're going to use. We can use similar triangles, trig functions, a lot of different things we're going to see in this chapter. And that's what changes per problem. All right, this is just an introduction to this problem. Now let's actually do the problem with these things in mind. So step 1, draw a picture if possible. I don't know if a picture is going to be terribly helpful here, but let's just do it. We have some balloon. We're pumping air into the balloon. We have a radius. We have a volume of the balloon. I don't know, there's much to do with the picture there. But we can say that r is going to be the radius. V is the volume. And note that we want to find dr dt when r is equal to 10. That's what this when the radius is 10 centimeters thing is talking about. And we are given that dv dt is equal to 5 centimeters cubed per minute, always. So in each of these problems, we're going to be given some rate, and we want to find some rate. The equation we're going to use to relate those 2 variables is the volume of a sphere. That is 4/3 pi r cubed. And note that we could write this as volume as a function of t is equal to 4/3 pi r as a function of t cubed. We're going to say these things are the same, but we're not going to write the of t part because it just gets more complicated. But that's what those variables mean. They're functions of t. So when I want to take the derivative of that, I'm going to take the derivative of both sides, the derivative of v, which is the derivative of v of t, equals the derivative of 4/3 pi r cubed. And again, r is a function of t. So this is implicit differentiation. The first point is we have dv dt on the left. That's what we are given. That's 5 centimeters cubed per minute. So we're going to plug that in at the end. And on the other side, we have to do this implicitly. So we have a constant we can bring out in front, 4/3 pi. And then the derivative of r cubed, we have to use the chain rule. We take the derivative of something cubed, which is 3 something squared. We leave the inside alone, r, and then we multiply by the derivative of the inside. And note that we are trying to find, this is what we are looking for. So now we've taken the derivative. Now I want to try to plug in the values and solve for the unknown rate. Our values that we have are that dv dt is equal to 5 centimeters cubed per minute. And we have that we are looking for this point when the radius is equal to 10 centimeters. So here we have dv dt is going to be 5 equals 4/3 pi 3/10 squared times dr dt. And we're looking for dr dt there. So we're going to divide by all of that. We have, we'll do some simplification real quick. We have a 3 in the denominator, a 3 right there. 10 squared is 100. So this is all going to be written as 5 equals 400 pi dr dt, the derivative of the radius. And we can write everything as the derivative of the radius is 5/400 pi. And the units are going to be centimeters per minute. And that is our answer. We found the rate at which the radius of the balloon is increasing when the radius is 10 centimeters. That derivative might be different if we asked for a different radius value. In fact, it would be. But that's going to be our radius value there, our derivative value. Let's do another problem to see the differences we can see in problem to problem. So here, completely different setup, but most of the stuff's going to be the same. Car A is moving west towards an intersection at 20 miles per hour. Car B is moving south toward the intersection at 30 miles per hour. At a certain time, car A is 30 miles away from the intersection and car B is 40 miles away from the intersection. At what rate is the distance h between the two cars changing at that moment? So step one, it's going to be important to draw a picture here. We have some intersection. And we have one car is moving west. It's moving west toward an intersection at 20 miles per hour. Car B is moving south at 30 miles per hour toward the same intersection. And at a certain time, car A is 30 miles away from an intersection, and car B, oh, sorry, that's car B I just labeled, sorry. Car B is 40 miles away from the intersection, and car A is 30 miles away from the intersection. At what rate is the distance h between the two cars? That's a different distance. That's looking for this distance is h. And at what rate is the distance h between two cars changing at that moment? So we need to define our variables, what's actually going on here. One of our variables is kind of defined for us. H is the distance between the cars. Between car A and B. And note that this is what we are trying to find. We're trying to find dH dt. The other variables are a little more hidden, but we're going to try to explain what they are. The first one is the distance from the car, the distance from car A to the intersection. And note that we have that the derivative dx dt is equal to 20 miles per hour at that time. Y is going to be the distance from car B to the intersection. And note that we have that dy dt is equal to 30 miles per hour. So here we're given the rate of two different variables, and we're trying to find the rate of a third variable at a certain time. At this point, it might be worthwhile to redraw this picture to make it a little simpler to kind of see what's really going on. So here we have h is the distance between our two cars. We have this point represents car B, this point represents car A, and this represents the intersection. X is the distance representing from car B to the intersection, or that's Y, car B to the intersection. X is from car A to the intersection, H is the distance between them, and note that we have a right triangle here. So what many students get in trouble here for is that they do try to plug in values like car A is 30 miles per hour away and car B is 40 miles away. That's X equals 30, Y equals 40 into equations before the end of the problem. That will be the absolute last things that we plug in. We don't want to think about them at the moment. This is our picture that we really want to focus on. I do want to talk a little bit about the distances and why we know that variable represents the distances, this X and the Y especially. So remember, what is speed, right? What does 20 miles per hour mean, right? We are tracking, this is telling us how fast the distance is changing. So if we were running a marathon or something, and we had some distance to the finish line, then we could tell our speed by saying that we have some distance here, d. That's a terrible letter to use right now. Let's use just x. That's going to be the distance to the finish line, and our speed is just how much that distance is changing. Right, so our speed might be 10 miles per hour. That means that in 1 hour, x is going to decrease by 10. We're going to go 10 units toward the finish line there. All right. That may be something that you already recognize, but that can be a stumbling point for a lot of students. I want to make clear that's what we're tracking here, is how much a distance is changing. That's what the variables need to represent. Let's redraw this picture, and then we will talk about step 2. In fact, we'll write step 2 right now. So step 2 is, what is an equation that relates these three variables together? And in this case, that's going to be the Pythagorean theorem. X squared plus y squared equals h squared. All right, so let's go to the next page. We have our picture. Here's y. Here's x. Here's h. And we know that x squared plus y squared equals h squared. We are looking for dh dt when x equals 30 and y equals 40. And we are given dx dt equals 20 and dy dt equals 30 at the same points. All right, so step 3, take the derivative. And we're going to do that with respect to t. So we're going to do the derivative of x squared plus the derivative of y squared equals the derivative of the other side, derivative of h squared. And each of those we have to do implicitly. The derivative of x squared is not 2x. We have to do it implicit differentiation. That's going to be 2 times x times the derivative of x, dx dt. This is going to be plus the derivative of y, which is 2y times the derivative of y, dy dt. And that is going to equal 2h times the derivative of h. So step 4, now we're going to plug in all of our values and solve for dh dt. Looking for dh dt here. So we have 2 times x is going to be 30. dx dt is 20. All right, we said x is 30, dx dt is 20, plus 2 times y. Y is going to be 40, and dy dt is 30. And that's going to equal on the other side 2 times, maybe we don't know what h is. We're looking for dh dt. So actually there is another problem here. We don't know what h is, but we can find it pretty quickly using the Pythagorean theorem. We have when x equals 30 and y equals 40, we have 30 squared plus 40 squared equals h squared. And that's going to give us that h is going to be equal to 50 when you do all of that out. You have to do a little bit more work to kind of plug in all the values there. So let's do everything now. We have 30 times 20 times 2 is going to be 1200. 40 times 30 times 2 is going to be 2400, equal to 100 dh dt. This is going to be 3600 divided by 100 equals dh dt. So what is happening here? We have our answer is 36 miles per hour. Let's make sure we actually answered the question. At what rate is the distance h between the two cars changing at the moment when they're those distances away? At that point, that distance is changing at 36 miles per hour. And it's getting smaller. So maybe you actually want negative 36 miles per hour, but we'll just say it's positive in the context of the problem. In the next video, we're going to do some more practice problems with different equations to relate variables together so we can get more experience with dealing with these related rates problems.